Hi and welcome to Unit 2, Topic 1, Video 5. In this video we're going to look at the Moivres theorem, which you won't have heard of before, and unfortunately, due to the order that we cover the topics, for this particular video series I can't provide the proof, but we'll look at the proof in Unit 3. For now, in the future, maybe the topic's been rearranged and we can provide the proof, but for now I haven't. So I'm just going to tell you that the Moivres theorem is this. R cis theta to the power of n is equal to r to the n cis n theta. Now, just to show you what this might look like, it means, if we expand that cis theta out, means that r cos theta plus I sine theta to the power of n, the whole thing, is equal to r to the power of n cos n theta plus I sine n theta. Now, you may have seen the trig topic already, or we've certainly already talked a little bit about the addition formula in the trig topic, the sums of angles, but you'll see if you expand this left hand side bracket, we do get something that then can be simplified to work for us. And we'll see later on that we play with squared, cubed first, and we can build up the proof for n. Now the n goes on to the r pretty simply. That's the easy part. It's getting the n into the sine and cos that's the hard part. But it's true. I'll tell you it's true. There are other slight variants as well, such as that we might have something more like r1 cis theta 1 times by r2 cis theta 2. And so this is not a power, but a power is just like this, where r1 and r2 are the same. But this gives us a similar result in that we get r1, r2 cis theta 1 plus theta 2. But for this unit, we just need to know this particular result, which is the power n, and this specific result is de Moivre's theorem. And at this stage, you might not know where it comes from, but I'm going to show you how we can apply de Moivre's theorem. Okay, so let's start with example 1. Now, the first couple of parts of this example are pretty trivial. I'll create a little bit of space for part B. That'll take a couple of steps. But part A doesn't take much. Part A is just simply 2 to the power 6 cis 6 times pi on 3. And that's all we need to do. I'll simplify that. 2 to the power 6, of course, is 64 cis, and then this becomes 2 pi. Now, you might choose, because 2 pi is that nice number, you might now choose to do a little bit of simplification here. So I will do this, and then in fact I'll create a bit more space here, and I'll give a bit more room to do this simplification. This becomes 64 cos 2 pi plus I sine 2 pi. 2 pi is the same as 0 in this case. 64 cos of 0 is just 1, plus I times sine of 0, which is 0, and so it's just equal to 64. So it actually works out quite nicely for us in this sense, and that's just a bit of luck. It won't always be like that. Let's look at this second example now, which will take a little bit more work, but again, applying de Moivre's theorem, we do 4 to the power of 3, and then cis 3 times pi on 6, all over 2 to the power of 5, and cis 5 times pi on 3. Now, probably need a little bit more space. This is equal to 4 to the power of 3. I'm going to write this down as 2 squared to the power of 3. And this is cis of pi on 2. All over 2 to the power of 5. Cis 5 pi on 3. Okay, so up to this stage now, I'm probably going to have to create a little bit more space again. But I'm going to show you the adaptation. So you remember I mentioned that there is another rule here that, well actually I'll just go back up to it. This rule, and that rule can actually be adapted again, if I just take it and copy it, paste it down here, to give us a rule with division. So if I rub this, that'll rub the whole out, rub that out, and rub this out, and rub that out, if we divide those two, we actually get R1 over R2, and cis theta 1 minus theta 2. So that's a nice little rule that works there as well. Same sense as this. It's like doing a power of a half instead of squaring, or doing that division instead of multiplying is the same as multiplying by 1 over. So we get the same result anyway, just through our multiplication. So we're going to use that here. 2 squared to the power of 3 is 2 to the power of 6 divided by 2 to the power of 5, and then we get cis pi on 2 minus 5 pi on 3. Now you get used to that working with radians. So we get 2 to the power of 6 divided by 2 to the power of 5 is just 2 to the power of 1. And then cis pi on 2 is the same as 3 pi on 6 minus 5 pi on 3 is the same as 10 pi on 6. 3 pi on 6 minus 10 pi on 6 is negative 7 pi on 6. And that's the best we can do, except we could bring it around to the positive if we wanted to. So negative 7 pi on 6, well, this is negative pi, which is negative 6 pi on 6. So negative 7 pi on 6 is here, where that's pi on 6. This is 6 pi on 6, so it's going backwards. And that's actually the same as going this way, in this direction. And it's the same as 5 pi on 6. So we could write this down a little bit neater as 2 cis 5 pi on 6. There's our options there. But that's the answer to part B. And now we're going to have a look at our answer to part C, which I've also asked you to verify algebraically. And this is where it really comes in handy, because we've seen that division, and we could use a division here, but we could also use de Moivre's theorem if we convert to polar coordinates. So I'm going to convert this to polar first. So the first thing I'll do is calculate my r value for the numerator. R is equal to the square root of root 3 squared minus, plus 1 squared. And hopefully you can see that's the square root of 3 plus 1, which is the square root of 4, which is 2. And theta is equal to tan inverse of b on a. So in this case that's negative 1, the complex coefficient, over root 3, and that should come out as negative negative 1 on that, so negative pi on 6 for our first theta. Now I need to be a little bit careful here, because of course I'm dealing with an Argand diagram. It could be two results. Tan is negative in the fourth and also the second. So just to check, it's root 3, so that's positive real part, negative complex part. That means it's out and down. So we are in the fourth quadrant, and that angle is in the fourth quadrant. So I'm happy with that. The second one has a similar r because it's root 3 plus I, and theta is equal to tan inverse of 1 on root 3. And they're both positive, so this is definitely in the first quadrant, and we get pi on 6. And so when I put this back in here, this is equal to 2 cis negative pi on 6 over 2 cis pi on 6. So I apply that extra version of de Moivre's theorem. 2 divided by 2 is just, well, I wrote this 2 divided by 2 the first time. Cis negative pi on 6 minus pi on 6. That's equal to 1 cis, and this becomes 2 pi on 6 negative, which can be written, of course, as, I don't need the 1 there, just simply cis pi on 3 negative. And I could simplify that down into a Cartesian form, so that will become cos of negative pi on 3 plus I sine of negative pi on 3. Now cos of negative pi on 3, we're still dealing with over in this fourth quadrant, keep in mind. And cos of pi on 3, so cos is actually positive in that fourth quadrant. So it's the same as cos of pi on 3, which is cos of 60. So this is equal to a half. And then over here, I've got sine of negative pi on 3, but sine's negative in the fourth quadrant. And it's root 3 over 2 is the exact value. So minus root 3 on 2i. Now, it did say verify algebraically. So my verification algebraically, which I'll just do over here in purple. It's root 3 minus I over root 3 plus I times by the conjugate, root 3 minus I over root 3 minus I. And hopefully you can see that this simplifies. I've got a perfect square on top, so I get root 3 squared plus 2 times root 3 times minus I, and then I get plus I squared, and on the bottom I get root 3 squared, that's the difference of two squares, minus I squared. Simplifying this, on top I get root 3, minus 2 root 3 I minus 1, I squared is negative 1, and the bottom I get 3 plus 1, so I'm taking my time here. 3 minus 1 is 2 minus 2 root 3 I over 4. That simplifies to give a half minus root 3 on 2i. If I zoom out now, it's exactly the same as what I just got here. Now you notice here I went to Cartesian form because, to be honest, and they're both about as quick as each other, but I find it a bit easier to just take this guy into Cartesian form than to move this guy into polar form. That's just me. So if I'm doing something that's a show that, verify algebraically, prove two things are equal, well, for me the choice is to go to Cartesian form, but really it's up to you unless you're specifically told.